Okay, so we're going to look at the two-dimensional wave equation in polar coordinates here. So the two-dimensional wave equation in rectangular coordinates, excuse me, is so that's the two-dimensional wave equation in polar in rectangular coordinates. So in polar coordinates, I want just let me scroll down. There we go. We need to change this part so what do we get when we make that change? And I'm not going to do the change itself because it's long and just a big chain worlds, actually. But you get this. So that's the polar coordinate version of this. And remember that for polar coordinates, the point x, y in the plane, you can draw a nice little triangle there. This distance is x, this distance is y. In polar coordinates, this angle is called theta, and this distance is called r. And then r squared equals x squared plus y squared, and tangent theta equals y over x. And so that's the relationships between polar coordinates and rectangular coordinates. So for the two-dimensional wave equation in polar coordinates, what we want to deal with is a circular membrane. So we'll have a domain. We'll have 0 less than r less than a, and we'll have 0 less than theta less than 2 pi. So those are our domains, t greater than 0. We have some restrictions on this because of polar coordinates. In particular, we need that u of r theta t has to be 2 pi periodic, at least, in theta, right? Because if we're just going around a circle every 2 pi, you should get back to this exactly the same place. So if u is our function of r theta and t, that's a solution to the equation, it has to be a function that's periodic in theta. And we also need a bounded solutions. There should be some number, some positive number, so that the absolute value of u is always less than that positive number. And we'll talk about that a little bit when we get to talking about what the idea is of this particular problem. We have a boundary condition. Which is when r is equal to a, we want it equal to u equal to 0, and we have initial conditions as well. So when t equals 0, r theta u of r theta 0 equals some function of r and theta, and ut of r theta and 0 equals some other function of r and theta. So the idea of what we're dealing with here, imagine a drum head, which is circular, of radius a, and u then is going to be the movement of the drum head up and down. So you have to imagine that this is the top, and you have a drum, right? However a drum looks like. And this is the top of the drum. And it's been nailed down at the sides. So the boundary condition so all the way around the edge here, whatever the drum is, it's been nailed down. And in the initial conditions, is you're given some kind of initial position, which is f of r comma theta, and you're given some kind of initial velocity, which is the gr of theta. Imagine that you struck the drum or hit it or something, and now it's vibrating, and you want to know what's the shape of the drum head as it vibrates. And so you have initial position, initial velocity, and then this is the differential equation that you need to solve. So how do we solve this? Well, we use our usual method, separation of variables. We'll set u to be a function of r, times capital theta, which depends only on theta, times capital T, which depends only on little t. You plug that into the PDE, and you get r theta second derivative with respect to time equals c squared second derivative of r times theta t plus 1 over r first derivative of r theta t plus 1 over r squared r second derivative theta with respect to theta times t. And then we'll start separating the variables by dividing through by c squared r theta t. And that'll give us on the left side tt over c squared t. And on the right side, you'll get r sub r over r plus 1 over little r sub r over r plus 1 over r squared theta 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 over theta. Second derivative of theta over theta. So, great. So the left-hand side depends only on t. Right-hand side depends only on r and theta. So left-hand side has to be equal to the right-hand side, which means they both are equal to the same constant, which we'll call K1. And that gives us a differential equation for t. If we solve this for t, we get d squared t dt squared minus k1 c squared t equals 0. That's our Arnold differential equation for t. And then you get an equation that involves both r and theta equals K1. Okay, so to separate this, which is what we want to do now, we're going to multiply through by R squared. And so we end up with that. And note that this term depends only on theta, while all the other terms depend on R. So that should be a minus because I'm going to move this over the other side, equals K2 equals minus theta, theta, theta over theta. So that separates the R's and the theta, and we pick up a second separation constant, which is K2. And so we have an equation for theta, which is d squared theta, d theta squared, plus K2 theta equals 0, with the requirement that theta of theta plus 2 pi has to equal theta of theta. In other words, that the function in theta has to be periodic with period at most 2 pi. It could be periodic with period pi, or it could be periodic with period pi over 2, but it certainly has to obey this relationship. And the other equation we get is the equation for R. So R squared d squared R dr squared plus R dr dt minus K1 R squared plus K2 R equals 0, and the boundary condition is R of A equals 0. So there's our differential equation for R. So, right, if we take this equation, we can move the K2 over to the left, and then we multiply everything through by the capital R to get this. Okay, so there's our various equations. What we won't need to do is solve the ODEs. And use, I guess we'll just say, and evaluate the separation constants. Okay. So we'll start by solving for theta. Right, and our equation was d squared theta, d theta squared, plus K2 theta equals 0, and theta of theta plus 2 pi has to be equal theta of theta. And there's 3 cases, as there often are for these kinds of equations. Case 1 is K2 could be less than 0. And if you solve that, you get exponential terms. And that fails periodicity. If you set K2 equal to 0, you get a linear term. And that also fails to be periodic. So you get only trivial solutions there, except if K2 is equal to 0 and theta is equal to a constant, then that is a solution to this, right? Because the second derivative constant is 0, and if theta is, if K2 is 0, you get that. And constant functions are actually periodic with period whatever you want, actually, because a constant function is a constant. So we get a constant function out of the K2 equals 0 case. And the most interesting cases K2 is greater than 0, which means that your solutions are going to be C1 cosine square root of K2 theta plus C2 sine square root of K2 theta. Right? So if we take theta of 0, that's just C1, and theta of 2 pi is C1 cosine square root of K2 times 2 pi plus C2 sine square root of K2 times 2 pi. And these two things have to be equal to each other. Right? And the problem is, what is square root of K2? If square root of K2 is not an integer, then these two things are generally not equal to each other. So we require square root of K2 to be an integer, which we'll call m, or K2 is an integer squared. And so we've evaluated the second separation constant, and we end up with theta sub m of theta equals C1 cosine m theta plus C2 sine m theta to meet our periodicity equations. And note, if we take m equal to 0, get theta sub 0 of theta, and that's just going to be C1. And so by letting m start at 0 instead of 1, we can include the constant case that we actually picked up from setting K2 equal to 0. So the solutions then to the equation for theta is this, and we allow m to start at 0. Okay, so then we'll look at the equation for r. Is r squared d squared rd r squared plus r dr minus k1 r squared. And now we know K2 is m squared, so we'll put that in there, times r equals 0. Great, and this is a Bessel's equation. Lots of different types of Bessel's equations. Because of the m, we're going to end up involving the mth Bessel equation, Bessel function for m greater than or equal to 0. So, and again, we're not going to talk exactly what the functions Jm are. We will point out that every function J sub m looks like a decaying exponential, although it's not, and it actually has a bunch of different zeros. Oops, we'll put that one out here, dot, 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 and some 0 out there. And this is alpha m1, so it's the first positive root of the mth function. This is alpha m2, and then this one would be alpha m3, right? The third positive root of the mth function. And then this is alpha mn, which is the nth positive root of Jm. And so that's what alpha mn is. The solution to this ODE The solution to the ODE is, sorry about that. On the one hand, the solution to the ODE involves this constant that comes from the ODE. On the other hand, we also know that the solution involves these roots. Remember that A is the radius of the disk that we're dealing with. And so that gives us a relationship between K1 and the roots of our functions. So we've now evaluated the second equation, which is K1, and that becomes that. So the equation for R turns out to be R squared d squared R dr squared plus R dr dr plus alpha mn over A, because that's my K1, squared minus m squared times R equals 0 with solutions that depend on m and n. So it's the mth Bessel function, went like that. And so there's our solutions for R. And then finally, we have the equation for T, which was d squared T dt squared plus c squared K1 T equals 0. Oh, minus c squared K1. Given that we now know what K1 is, this becomes C alpha mn over A in that quantity squared times T equals 0. And so we have T mn, our solutions to that differential equation are Cmn cosine of C alpha mn A T plus d mn sine C alpha mn over A T. So those are solutions for T. So now we can create our normal modes. They depend on the two integers umn. And that's going to be Rmn times theta, which depends only on m, times T, which depends on m and n. And this is a pretty long expression, so I'm going to write it out in a couple of different levels, I think. So R is Jm alpha mn over A times R. And then theta m is am cosine m theta plus bm sine m theta times tmn, which is cmn cosine c alpha mn over A t plus b d mn sine C alpha mn over A T, close bracket. Great. And so then our solutions. So the series solution is U of R theta T equals the double sum m equals 0 to infinity, n equals 1 to infinity of our normal modes. And so that gives us the series solution. Problem is that we have lots and lots and lots of coefficients floating around, and we want to know what are these coefficients, right? That's the second part of solving this. So I'm going to split U into two parts. And what we're going to think about these parts U1 and U2 is this is the response to the initial position, right? If we're thinking of this as a drum, we want to say, well, you pull it a little bit or you move it away from its equilibrium and you get a response due to that. And then you'll also get a response to the initial velocity. And we'll separate those two out. So what is U of U1 of R theta T going to equal? That's the response to the initial position. Remember, the initial position is when T equals 0. And when T equals 0, these sine terms are all equal 0. So when T equals 0, you pick up these cosine terms here, but you don't pick up the sine terms. So U1 of T is this whole mess with just the cosine terms. So that's going to be Jm alpha mn over A times R. That's our R part. And then the entire theta part, Am cosine m theta plus Bm sine m theta, and then just times the cosine part of the time equation, which is Cmn cosine of, no, what was the coefficient there? C alpha mn over A T. Great, so there's U1. It just involves the cosine part of the time equation. And we can rewrite that a little bit as Jm alpha mn, let me undo that. The mn is supposed to be subscripts, and they keep creeping up into my formula. And we're going to combine these coefficients, right? If I distribute the Cmn in, we'll have a cosine C alpha sub mn T over A times Amn, which is our Am times my Cmn, cosine m theta plus B mn sine m theta. And the goal is to figure out what these two things are. So we know that U1 of R theta and 0 should be our initial position, which was F of R theta. So so we get F of R theta. Oh, and this is a double sum. I forgot to put that in there. Equals sum m equals 0 to infinity, sum n equals 1 to infinity, Jm, Amn let me undo a little bit of that and think through what I'm doing. Okay, so setting t equal to 0 means that this term becomes 1. So I end up with Jm alpha mn over AR times Amn cosine m theta plus Bmn sine m theta. And I want to figure out what the AMNs are and the BMNs are. So how do we go about doing that? Well, we're going to set up two different inner products. right? Because usually we deal with these with inner products. So we'll set inner product 1 of two functions. And here f and g are just two functions. They don't represent the initial condition and the initial velocity. I'm just using them as variables. And this will be product 1. We're thinking this is an inner product involving the theta terms. So the first inner product is just this, and we know that the set of functions 1 cosine theta, sine theta, cosine 2 theta, sine 2 theta, dot, 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 right? Cosine n theta, sine n theta. We know that that collection of functions these are mutually orthogonal with respect to that inner product. And we know that the inner product of, say, sine m theta equals pi. Right? Just do the integral. So if you have the same m, we get that. And that the inner product of 1 with itself is actually 2 pi. Great. So how do we figure out what some of these coefficients are? If we take inner product of f with a function, say, for example, cosine I theta, right? That becomes the double sum m equals 0 to infinity, sum n equals 1 to infinity of that whole thing, because this is f is this whole thing, j m alpha m n over a r times a m n inner product of cosine theta, cosine m theta, cosine I theta. And then we can put a bracket around that. Okay, so what did actually just happen here? So we wanted to take the inner product of this function up here, which is this long formula, with cosine I theta, which is one of these functions that we know are mutually orthogonal with respect to this inner product. And so this is the inner product 1 here and here. So when we take the inner product, we know that the inner product is linear, which means we just take the inner product with each term. And so this doesn't involve any thetas at all. So it's just basically the role of a constant. This is a constant. Cosine m theta, when we take the inner product of that, we have to think about whether or not m is equal to I. But we know that sine m theta, when you take the inner product of cosine I theta with sine m theta, you definitely get 0. So you end up with just these terms. And we know that cosine I theta inner product with cosine m theta equals 0 unless m equals I. And cosine I theta equals pi. So what do we end up with here once we've done our inner product? F inner product with cosine I theta is going to be, well, m is set up to be I, so this sum goes away and we're left with the sum n equals 1 to infinity j sub I alpha sub I n over a r times a I sub n times pi. So we have this series, and we're still looking for these things. So what I'm going to do is I'm going to call this some function of r, because it is. We've got r's floating around there. We've dealt with the thetas, but not the r. And we'll introduce a second inner product. So this is a second inner product, which we're thinking about for the r's. And what we know about the Bessel functions, ji is ji of alpha I n a r, comma ji of alpha I m. I shouldn't use n. We'll just use an n prime over a r equals 0 for n not equal to n prime. So these things here, these things are actually orthogonal under this inner product. If we actually have the same root, alpha I n over a r, that turns out to be a squared. I'm not going to draw this because that would be for, of course, on Bessel functions. Alpha I n just be an n. And so that's what you get there. So what we have then is we have another inner product. We have another series. We want to peel off these coefficients. So what do? If we call this whole thing the result of the first inner product, if we call that kr, then we want inner product with respect to r, kr against, say, j sub I, alpha sub I j. So let's pick a particular value for n there, over a r. And that will be this, inner product 2. And that will be the sum, n equals 1 to infinity, of pi times a sub I n, that's these two terms, inner product of j sub I alpha sub I n over a times r with j sub I alpha I sub j over a r. And so what do we get out of that? Well, if n does not equal j, that's inner product 2, then the inner product equals 0 because these things are orthogonal. So we end up with k of r ji alpha ij over a r bracket 2 equals pi. So now we're setting n equal to j. That's the only thing that survives, ij. And then this whole mess turns into that. Great. So after all that, what does this equation tell us? It actually gives us an equation for aij, which is all the a terms. So aij is 2 over pi a squared ji plus 1 alpha ij times inner product 2 of kr ji alpha ij over ar. That's just rewriting this equation. Now, if we rewrite that inner product, this is the integral from 0 to a of k of r times j sub I alpha sub ij a r close parentheses, there should be parentheses there, times r dr. But kr itself was defined as an inner product, right? We defined kr here. And that's the inner product of the function, the initial condition, f with cosine I theta. And that is an inner product 0 to 2 pi of f r theta cosine I theta d theta. So if we plug that in, we get aij is all this coefficient out front, times the integral from 0 to a, and now k of r is this function of r, so the integral from 0 to 2 pi of f of r theta cosine I theta j sub I alpha ij over a r d theta dr. And so that gives you a formula for how aij. So double inner product there. We had a double sum, so we had to use inner product twice, once to deal with the cosines and sines, once to deal with the Bessel functions. They have their own inner products. So we had to use two different inner products, and then we end up with this double integral. And then you can do the same things, same sort of thing, inner product with sine to get the BMN. And you can do an inner product with just one to get the case where m equals 0. And then if you want the response to the initial velocity, that would be the sine terms here. And you'll have coefficients CMN and DMN, and you do the same procedure with the initial velocity g of r theta. And that gives us the solution to the wave equation in polar coordinates.